Hi, I'm John Doherty, and in this video I want to talk about a new method that's just become available through the PEST HP suite, which I've named Ensemble Space Inversion. But before I talk about Ensemble Space Inversion, just a little bit of revision about things that have been covered in other videos. And the thing I want to talk about first is, why is it important to use lots of parameters when we history match a groundwater model? Well, normally when we history match a groundwater model, we've got a medium to large area with some data in some places, and that data is often rich locally in information about hydraulic property heterogeneity. And our job in doing history matching is to listen to that data. Now, we don't know exactly what it's going to tell us. We don't know exactly where it'll say the history matching process will say that heterogeneity exists in hydraulic properties. So we shouldn't really say, I'm going to use zones of piecewise constancy, especially if they're broad. We let the data speak. We let the data tell us where the heterogeneity should exist, with constraints exercised on the history matching process, of course, so that we don't overfit or we don't come up with stupid parameters. But we let the data speak, and we have parameters lying in wait wherever the data may suggest that heterogeneity may exist. That way, we capture whatever information is available in the data pertaining to hydraulic property heterogeneity. And what do parameters do? They're sort of receptacles for information that's contained in field data. We don't know what that information is, so we have lots of parameters available to receive it, so we don't bias that information as we listen to what the data says. That's the first reason. The second reason is that there's no way that in just about any context in which we calibrate a groundwater model that we're going to have parameter uniqueness. The data cannot tell us everything that's under the ground. So when we make predictions, there's going to be uncertainty. And for reasons we've talked a lot about in other videos, we need to quantify that uncertainty. Therefore, the fact that we cannot estimate all these parameters uniquely requires that we represent the repercussions of their non-uniqueness on any prediction that we care about. That is, the parameters we cannot estimate uniquely are just as important as those that we can. So, another reason for having lots of parameters, reducing bias in history matching and quantifying the repercussions of information insufficiency in our calibration dataset. So, how is history matching normally done? Well, there's two broad approaches to history matching, which I'm sure most of you are familiar with. The first approach, which has been around for the longest time, is model calibration. Again, this is a subject of other videos, what we should aspire to when we calibrate a model. What we should aspire to is to come up with a minimalist solution to the inverse problem. A solution to that inverse problem which gives me parameter fields and predictions of minimized error variance. So we start off with a simple parameter field, perhaps the mean parameter field from the prior probability distribution parameter set point of view. And then we say to PEST, please fit the data as well as we're entitled to fit the data. But in doing this, deviate from this minimalist, this homogeneous perhaps parameter field, only to the smallest extent required to allow you to fit the data. We use numerical regularization to achieve this, and often this will be based on the prior probability distribution of the parameters. So we say, to the extent that you need to introduce heterogeneity to this parameter field PEST, do it in a way that conforms with what I think is happening under the ground, given the nature of the geology that prevails in this study area. So if we do everything right, we then end up with a minimalist, minimum error variance parameter field that hopefully allows us to make predictions of minimum error variance. Now this doesn't mean they're right. This doesn't mean that the error variance is even particularly small. It just means that it's as small as it can be given the information content of the data. We've made our potential for error symmetrical with respect to any predictions we're making. So that, in a nutshell, is model calibration. But then, especially more recently, people are using ensemble smoothers a lot more. The mathematics behind them is fairly similar, but they achieve different objectives, and there's a video about the mathematics behind the ensemble smoother in this series. So here we bring geostatistics into play just a little earlier. We use the prior probability distribution of the parameters to come up with samples of the prior probability distribution, random parameter fields which are all in conformity with what I think is the nature of hydraulic property heterogeneity. I use an ensemble smoother like PES-PPIES, and PES-PPIES adjusts these parameter fields, these samples of the prior, so that eventually they become samples of the posterior parameter probability distribution. When a prediction is made, that prediction is then made many times so that the posterior probability distribution of that prediction is sampled. Now, a couple of little mathematical facts here. If we do not use localization, and localization is an option when we're using ensemble smoothers, but if we don't, then every one of these final parameter fields is actually a linear combination of the original parameter fields. So this is a certain linear combination of the samples of the prior combined in a certain way that gives us a sample of the posterior. Different linear combination for the second, different linear combination for the third. So what are the advantages of these two different approaches to history matching, the strengths and weaknesses? Well, calibration, I think, has got some wonderful advantages, especially when we're developing a model, building a model. We don't history match once, we history match many times. And every time we do, we're finding stuff out about the conceptual basis of our model, about the conceptual basis of our prior parameter probability distribution, about the integrity of the data. The first few times we history match, we don't get very good fits, so we modify the model, modify the prior, decide whether we like this data or not, whether perhaps a head should be assigned to another model layer rather than the one it's in. So the ability to get this simplest solution to the inverse problem, which, if it turns out to be complicated and horrible and we don't like the parameters, or we just don't get a good fit, it's fairly easy to identify what may be wrong with the model, the current conceptual basis, or the data, and then we can make adjustments and then do it again. And to help with this process, normally when we calibrate a model, we calculate a Jacobian matrix that gives us sensitivities. And sensitivities, what model output is sensitive to what parameter, can often help us resolve why I can't fit two different aspects of the data at the same time. So the sensitivities are a lovely little byproduct of the calibration process. And then when the model is built, we have our minimum error variance parameter field and the capacity to make predictions of minimized error variance, and then do other nice things with linear analysis such as linear data worth analysis. The bad thing about calibration is, well, it's expensive, and if we've got a highly parameterized model and we're calculating derivatives using finite differences, we have to do an awful lot of model runs, and this is going to cost us dearly if we've got a lot of parameters and if that model takes a long time to run. Ensemble methods. Well, the beauty about ensemble methods is the numerical burden of their implementation is so much less. The number of runs per iteration of the inversion process is proportional to the number of realisations in the ensemble. and this needs to be something above the dimensionality of the solution space. And the dimensionality of the solution space is roughly equal to the number of independent pieces of information in the calibration dataset. So ensemble methods use this dimensional reduction, as it's called, to work only in a subspace of parameter space comprised of samples of the prior to solve the inverse problem in that space. And then uncertainty analysis is woven into the very fabric of the inversion process. The not so good things, well, I find it's a little bit hard to undertake that laborious process of model refinement. Yes, we can look at things like prior data conflict, but listening to the data and perhaps telling us through stupidity of parameter values or failure to get a good fit where the conceptual basis for the model is in error, sometimes it's a little bit hard to work out exactly what to do next, because we're not seeking that minimalist solution to the parameter, to the inverse process, and so the message of what may be wrong with the model and what needs fixing with the data or the model may get a little bit lost in realisation mist. Also, as soon as we're working in a reduced dimensional subspace, there is a possibility of parameter and predictive bias. The more realisations we use, the less is that chance, but this is something we've always got to be careful of. Sometimes using ensemble methods, the ability to get a good fit with the data isn't that great, especially if the problem's highly nonlinear. And then, even though we get uncertainties, well, those uncertainties are only indicative. Sometimes they're inflated because we haven't got that great a fit with the calibration dataset. Sometimes they're too small because of ensemble collapse. This isn't to say that we shouldn't use ensembles or anything like that. We just have to know the strengths and weaknesses of the different methods. Ensemble methods are fast and allow us to work with lots of parameters, but of course, with benefits always comes some cost. There is one thing for sure, however. If we've got a great big model, with great big run times, and lots of structural complexity, which we should match with parameterization complexity, we don't have too many options. We have to use some kind of dimensional reduction method if we're going to history match that model. Iterative ensemble smoother is one methodology to do that. Another methodology to work in a reduced dimensional subspace with a highly parameterized, structurally complex model is ensemble space inversion. And that's what we'll talk about now. Ensemble space inversion has 5 defining features, which we'll now briefly talk about. Its first defining feature is that, like ensemble smoother methods, it works in a reduced dimensional parameter space. Like IES, that reduced dimensional space is comprised of realisations of parameters and more. We'll talk about that in a moment. But the bottom line is, through employing this dimensional reduction scheme, through working in a subset of parameter space, we have the same model run efficiencies as that which an ensemble smoother has. The number of model runs required per iteration of the inversion process is much, much less than the number of parameters that are being estimated. It's only equal to the dimensionality of the subset of parameter space in which we're working, and that is only as large as the information content of the calibration data set. So the good things about that is that we have this incredible model run efficiency that comes with methods like IES. The bad thing is that, as with all dimensional reduction methods, whenever we do work in a subset of parameter space, there's always the risk of some parameter and predictive bias, with that risk going down as we increase the dimensions of the parameter subspace in which we work. The second defining feature of ensemble space inversion is that it seeks a unique solution to the inverse problem. Unlike IES, it does not attempt to sample the posterior parameter probability distribution. In contrast, it uses Tikhonov regularization to try to ensure that we obtain a unique parameter field that has the properties that we desire from uniqueness. That is, a minimum error variance solution to the inverse problem, minimum error variance as far as we can achieve this within the confines of the parameter subspace in which we're working. As we'll talk about in a moment, we have considerable flexibility in how we use that subspace. So the good things about that is we have the advantages of calibration. And as we said a little while ago, these advantages can really help us as we construct a model, as we're exploring whether the conceptual basis of the model is correct, whether the data is of high quality. So we get to do rapid calibration many times, testing concepts on which the model is built. And we get sensitivities out of this process, and this can help us identify where concepts or data may be in error. And at the end of the process, we have sensitivities as well, and this can help us to create plots or indicators of what parameters are well estimated and what parameters aren't, given the data we have at hand, given the data that forms the calibration data set. The bad thing is, of course, that calibration is only calibration. We don't get to quantify the uncertainty of those parameters, nor the uncertainties of predictions which are sensitive to our parameters. That has to be done in a separate step. Well, not quite. Nonlinear uncertainty analysis has to be done in a separate step. We can do linear parameter and predictive uncertainty analysis together with the ensemble space inversion process. So to look at this pictorially, we are calibrating the model. We use the geostatistical descriptors of our parameters to generate realisations of parameter fields. We then use ENSI to manipulate those fields using Tikhonov regularization to seek a minimum error variance solution to the inverse problem. To acquire a minimum error variance parameter field, which then allows us to make predictions of minimum error variance. ENSI actually calculates the factors through which these realisations are combined to derive this final minimum error variance parameter fields. And calculating these factors directly has certain advantages. In fact, calculation of these factors directly is the third defining feature of ENSI. By calculating those factors directly, we use finite difference derivatives, and we can normally, unless the model behaves badly, obtain derivatives with fairly high integrity. This means that we're able to achieve, hopefully, as good a fit with the calibration dataset as we can when working in our parameter subspace. So we normally get a pretty good fit with the calibration dataset. As well as that, we have certain other features that come with this type of regularized inversion. For example, we can use Broyden-Jacobian update, if we're using PEST HP as we should, to enhance the ability of the inverse problem solution process to find a minimum error variance parameter field, to attain a good fit with a calibration dataset, even in highly nonlinear situations. So we can use all the good things that come with gradient-based solutions of the inverse problem to obtain a good fit with the calibration dataset under possibly difficult circumstances. At the same time, by using PEST HP to estimate these realisation factors, we're able to use its advanced regularization functionality to obtain the minimum error variance solution to the inverse problem, At the same time, we prevent overfitting through use of the target measurement objective functionality that comes with PEST-HP's implementation of Tikhonov regularization. And there are practical benefits as well. For example, if we've got a structurally complex model and lots of parameters, often there can be model run failures. If we're using IES, we either lose a realization when this happens or the realization doesn't get upgraded. If we're doing things using PEST-HP, model run failure will normally happen when we're testing parameter upgrades. We just abandon that upgrade and go to another. We don't lose a realization, we don't lose a dimensionality of parameter space. The bad things about directly estimating realization factors is that unlike ensemble smoothers, we don't get to use localization to increase the dimensionality of the parameter subspace in which we're working. However, in ways we'll talk about in a moment, we get to use our parameter subspace quite efficiently, more efficiently in fact than IES. Which brings us to our fourth defining feature of ensemble space inversion. This is the flexibility in which we can define the subspace of parameter space in which we are working. Different parameter types can be divided into different groups, and the realizations which we generate can be separate for those different groups. So we're not, for example, hardwiring values of hydraulic conductivity and storage, for example, into the one realization, and then in another realization we have different values of hydraulic conductivity and storage hardwired into that realization, and everything has to be adjusted together, all hardwired into each realization. Now, the good things about being able to generate separate realizations for separate parameter groups is the flexibility which it gives us, particularly if we're in nonlinear inverse problem circumstances. By adjusting different parameter types separately, or the factors applied to the realizations of those different parameter types, we can have more realizations for one parameter type than another if that parameter type affects more observations, but by separating them we also accommodate nonlinearity of the inverse problem. So, to look at it pictorially, we're undertaking model calibration. We use the geostatistics pertaining to our parameters to generate realizations sampled from the prior. One set of realizations for one parameter type, another set of realizations for another parameter type. Then we use PEST-HP to derive, using Tikhonov regularization, a minimum error variance parameter field which has parameters of different type, which allows us to make a prediction of minimized error variance. Behind the scenes, PEST-HP is calculating factors through which these parameters are combined to produce this subpart, this subspace of the final parameter field, and then evaluating factors through which these realizations are combined to calculate this component of the final parameter field. The final defining feature of ENSI again pertains to the flexibility with which the subspace of parameter space in which we are working can be defined. Not only can we include realizations of parameters of different types, we can also include individual parameters. And this can be extremely useful under certain circumstances, particularly if those parameters are, for example, mean values of different parameters in different layers, or if you see some of the other videos in this series, if we're using conceptual points where we define parameters, so-called hyperparameters, which govern the geostatistics of our real parameters, for example, the range, the correlation length of a variogram, we can estimate those at the same time as we estimate parameters which determine where heterogeneity will be introduced to a model domain. By estimating hyperparameters separately from realisations of hydraulic property detail parameters, the whole inversion process becomes much more linear and generally can converge to a good solution in a reasonable number of model runs. So the good things about being able to estimate parameters at the same time as we estimate realisations, particularly if these are mean parameters or trend parameters, so that the realisations can pertain to perturbations about those trends. The good things is that this gives us so much ability to cope with model inverse problem nonlinearity at the same time as it reduces the propensity for parameter and predictive bias. So we're using our subspace in the most efficient way to obtain a minimum error variance solution to the inverse problem of model calibration. Looking at it pictorially, we're undertaking model calibration. We use parameter statistics to generate realisations, and we include in the calibration process individual values of some parameters. We use PEST-HP to solve that inverse problem, Tikhonov regularization to try to ensure that it's solved in a way that leads to a minimum error variance solution to that problem, to obtain a parameter field with parameters of this type expressed by a minimum error variance solution for parameters of this type, a minimum error variance solution for parameters of this type, and a minimum error variance solution for certain individual parameters, which hopefully allows us to make predictions of minimum error variance. So PEST-HP is calculating sensitivities for these parameters individually at the same time as it's estimating factors through which these realisations can be combined to produce this aspect of the final parameter field, and factors through which these realisations are combined to derive this aspect of the final parameter field. So these are the 5 defining aspects of ensemble space inversion. So now let's have a brief look at the workflow by which all of these things can be achieved. So let's start by pretending that we're setting up for PEST-PP IES, that we're going to use the ensemble smoother. In this case, we need a PEST control file and we need a parameter uncertainty file. The parameter uncertainty file provides the geostatistics associated with the parameters that are featured in the PEST control file. If we're going to undertake ENSI-based inversion instead of using IES, we only need one extra file, and that file is called an ENSI specification file. Let's have a look at these files in just a little more detail. So here's the PEST control file, just a normal PEST control file, probably featuring lots of parameters. We're working with lots of parameters for the reasons we discussed earlier. We tell PEST to run in estimation mode. We don't run in regularization mode. The regularization which is used to achieve a minimum error variance solution to the ENSI inverse problem will be added automatically in ways we'll discuss in a moment. Here's an example of a parameter uncertainty file. The protocol for this file is described in Part 2 of the PEST manual. This file will normally feature a number of covariance matrices which are based on spatial correlation existing between spatially defined parameters. This covariance matrix can be built in a number of ways. Through the PEST suite, the groundwater utilities provide the ppcov family of utilities. PLPROC, the parameter preprocessor supplied with PEST, can create covariance matrices. Functionality is available through PyEmu. All of these packages allow you to base that covariance matrix on concepts of geostatistical stationarity or non-stationarity. Non-stationarity means that correlation lengths, correlation directions, and isotropies can vary in different parts of the model domain. This is just the subject of another video. The ENSI specification file is particularly simple. This is where we assign different parameter groups to different realisations. So we define the individual or groups of parameters which will be subject to realisations, for which we generate random realisations for realisation group 1 in this first section of the file. Here we define what comprises realisation group 2 and the number of realisations that will be used in the ENSI inversion process. And finally, if we include individual non-realisation parameters, they are defined in this bottom section of the file. So setting up this file is particularly simple. It can be done with a text editor in a matter of moments. Once we have these three file types, we run a little program that is supplied with the PEST HP suite called ENSI Prep or ENSI Prep. ENSI Prep builds a new pest control file from the old pest control file. This new pest control file features the new parameters with which we're working, the parameters which govern the subspace in which we are implementing the dimensional reduction as a basis for solution of the inverse problem. Realisation factors will be featured in this file, and also any individual non-realisation parameters that are inherited from the original pest control file. ENSI Prep adds prior information and regularization to this file. The other thing that ENSI Prep does is it writes the input files for another little program called ENSI Mod. Then it takes the original model batch file and adds ENSI Mod to that original model batch file. ENSI Mod calculates native model parameters from realisation factors. So whenever the model is run, ENSI Mod runs first and then the model can run. Now all this is done in a matter of moments. Once we have our three files that we talked about a moment ago, ENSI Prep does the rest. It builds the new pest input dataset, it builds the input files for ENSI Mod, constructs the new model batch file, all done for us. All we have to do is run PEST HP to achieve a minimum error variance solution to the inverse problem in ways that we've just described. For more details, there's a tutorial that's now downloadable from the GMDSI website. This focuses on a fairly simple model, which is also the subject of other tutorials, to make it fairly clear in simple terms how all this is done. But be assured that ENSI is also being used quite successfully in far more complicated cases with much larger models, with much larger runtimes, achieving some very impressive results. So, what can we conclude from all of this? Well, ENSI, I think, can help us undertake important parts of the overall decision support modelling workflow. During model construction and development, when history matching is all about refining the concepts on which the model is based, ensuring the integrity of the data, ensuring that the model is able to fit the data with reasonable parameter fields, repeated history matching, rapidly undertaken with ENSI, allows us to undertake that process of model refinement quite efficiently, using all the benefits that come through a calibration-based approach to model conceptual refinement and development that we talked about earlier in this video. We get to see fairly quickly whether a minimum error variance parameter field does in fact allow model outputs to fit field data, and if not, why not, possibly with the help of accompanying sensitivity analysis. At the conclusion of the decision support modelling process, we have a parameter field of minimum error variance that hopefully allows us to make predictions of minimum error variance. Yes, that parameter field will have a few bumps and lumps because after all we are working in a limited dimensional parameter dimensional subspace. There could be a little bit of bias there, but that's the cost of being able to do this at all, given the large number of parameters that a structurally complex model requires to do its decision support job. At the same time, at the end of the modelling process, we have a sensitivity matrix, a Jacobian matrix that we can use to provide statistics associated with the parameter field that we've just come up with, and can also be used as a basis for linear, parameter and predictive uncertainty analysis. But what about nonlinear uncertainty analysis? As we've talked about a lot in this series in other videos on the GMDSI website, when we're doing decision support modelling, it behoves us to quantify the uncertainties associated with decision critical predictions. Well, we have other methods available that will allow us to do that. For example, PPIES and data space inversion. They can be used starting from the calibration field that Ensemble space inversion has given us. That can increase their efficiency and alacrity in quantifying the uncertainties of parameters and decision critical model predictions. There's another video in this series about data space inversion. I really like data space inversion. Data space inversion is incredibly model run efficient in implementing its uncertainty, its predictive uncertainty quantification tasks. It also, I think, gives us possibly the best estimates of a prediction and the uncertainty associated with a prediction. And it does this through avoiding having to actually adjust parameters, which can often be a highly nonlinear process, and because of the extreme nonlinearities that often accompany parameter estimation, the uncertainties, the samples of the posterior that we end up with are somewhat biased and not really good samples of the posterior parameter probability distribution. By avoiding that step, often the uncertainties that we're associating with predictions have less bias and the uncertainty intervals have more integrity. So, data space inversion is great and it's efficient. The only problem with data space inversion is we don't associate parameter fields with particular predictions. So you could ask, well, if data space inversion can do everything, why do we need to calibrate at all? Why do we need to use ENSI? Well, there's a couple of reasons that I think we do. If we are going to use a model to analyse the uncertainties of decision critical predictions, even if those uncertainties are based on DSI, then stakeholders have to be sure that the model on which we're basing that has integrity. And it has integrity if it allows model outputs to fit past system behaviour. So that seems to be an essential component of the model construction process. A model that's conceptually correct and has been tested as such through history matching, that, when accompanied by a reasonable parameter field, allows model outputs to replicate what happened in the past. If we have a model and a parameter field that can do that, then we can't reject the hypothesis that this model is a good enough simulator to be used as a basis for decision support. So we can't really dispense with the need to find a set of parameters, a reasonable set of parameters that allows model outputs to replicate the past. And for reasons we talked about, this is what ENSI can do for us. We can get pretty good fits, as good a fit as we're entitled to, with a calibration data set using a complex, highly parameterized model. And then, when it comes to predictive uncertainty analysis, perhaps after we've calibrated our model using ENSI, we then use DSI to obtain samples of the posterior predictive probability distribution. And as for reasons I said a moment ago, I think often these have as high an integrity as we're going to get, because we avoid what can often be a problematical sampling of the posterior probability distribution of a nonlinear model, of a model for which the inversion process is nonlinear. DSI avoids that by going straight from the past to the future in ways described by other videos. What if we do this, and for a particular prediction of management interest, we find that, well, if we manage the system in a certain ways, perhaps there are some things could happen that we don't want to happen. Perhaps there'll be some management threshold for which there is a finite probability that things will go wrong, that we won't exceed that management threshold. We may then want to know, well, what could make this happen? What is the actual parameter field that could cause the things we don't want to happen to actually happen? And we're entitled to ask that. Well, perhaps this is another place that ENSI can help. Remember, DSI does not associate parameter fields with particular prediction. So if we want to associate a parameter field with a pessimistic prediction, we could use ENSI again. ENSI, as this video points out, enables us to get a good fit with a calibration data set with a minimal number of model runs. So if we now use ENSI to calibrate against what happened in the past, as we do when we normally calibrate a model, but also include in the calibration data set the thing that we don't want to happen in the future, we can obtain then a parameter field which replicates the past at the same time as it predicts something we don't want to happen, but still can happen and can't be ruled out according to the information that we have at our disposal at the present moment. So we can see the parameter field that could lead to management failure. This is good for didactic purposes. It can also help us in adaptive management and in design of monitoring networks or acquisition of more data prior to undertaking any contemplated development of an area. So that brings us to the end of this video. Thank you for listening.